Okay. Okay. So yesterday we covered branch prediction. We could go on and on in the fetch engines, but I want to switch topics and continue where we left off on DRAM. We may get back to control flow handling later on, but I gave you the basics of control flow handling, especially the branch prediction to begin with. I'm going to start with simulation because this kind of continues where we were at memory lectures. Remember, we talked about a lot of challenges, fundamentals in main memory, and then DRAM basics and operation, and then memory controllers. And then I want to talk about simulation. That's where we will take it. And then we'll talk about memory latency. But recall what we covered last time in the memory lectures. We wanted to design a memory controller that automatically found a good scheduling policy on its own. And we approached it from a reinforcement learning perspective. We saw that the DRAM scheduler seems very much similar to a reinforcement learning agent that interacts with the system, observes some state, takes some action, and based on that action receives a reward. And you could actually design the DRAM scheduler to associate system states and actions with long-term reward values such that it would choose a particular action at a given state that would lead to maximizing a particular reward. And we discussed this scheduler at some depth, and you can read the paper if you would like in more detail. I'm not going to get to this again. But that's the idea. And you can continuously update the reward values for each state action pair. I think this is a very good direction for systems research to pursue going forward, especially in architecture when it's difficult to design some of these controllers. As you can see, this is a relatively early paper on the topic. There's very likely to be many more research that will come in this direction, in my opinion. There's the other direction of accelerating machine learning, but that's already happening, as you know, right? So if you're interested in ideas toward this direction, feel free to develop them and talk with me also. But if you design something like this, then you always have the question of how do you simulate it, right? So that's why I wanted to lead into the future memory lectures with simulation. And this is going to be a short lecture on simulation because it's not only about simulation of memory, it's really about simulation of ideas in computer architecture. How do you evaluate ideas in general? And we're not even going to talk about only simulation, but we're going to focus on simulation because the key question is you have a new idea, you want to evaluate it somehow, and the system that you're going to evaluate it on doesn't exist, and the workloads that you may be really interested in don't exist also, right? And how do you do this? Basically, how do you assess an idea will improve a target metric X? You could decide you develop a new workload also, and we've done it as well. Other people have done it. That's also important. But assume that assume that the workload is constant for now. So there are a variety of evaluation methods available, and I'm going to start with theoretical proof. People do this evaluation, right? You prove that a particular algorithm provides you performance at some level. You could do analytical modeling, estimation. You could do simulation at varying degrees of abstraction and accuracy. We're going to focus a lot on this one. You could do prototyping with a real system, like FPGAs, or you could go implement the idea on a system that is going to actually be run, and you could look at its effects on real workloads that you can run. Right? So you can see that there's a progression over here. Theoretical proof is usually not easily available to architects or system designers. There are very few things that you can really prove about the systems that we design. And the interesting things that you really want, especially, will this improve performance and by how much will it improve? Because what we have is very much workload dependent. And you cannot model the workloads in some theoretical way easily. This is usually out of the architect's domain in general. Sometimes you could potentially, if you're trying to provide latency bonds, for example, you could look at the worst case latencies and try to bound those worst case latencies. You could potentially do something over there. But that's more like workload independent, right, if you think about it. If you're trying to bound worst case latencies, you should look at the worst case workload, which is really not the workloads that you have in general. Okay, so architects usually resort to some other techniques over here, and usually somewhere here in general. There's analytical modeling and estimation. You could say, okay, I'm going to have an analytical model for this DRAM system, let's say, and I'm going to model this controller. And I'm going to have inputs to this controller, and I'm going to get those inputs from the workloads. So that's possible, certainly, and we're going to see examples of this. But this is usually not that easy also, because to be able to form the analytical model, you should first of all really understand the system that you're modeling and build a model for it. And that model should be accurate, reasonable. So this is very interesting also. It's doable. And if you can do it, that's very nice. But it may not be easy, especially if you have very complicated workloads, right? If you have complicated workloads that are interacting with each other, you have to model them really well. And you have to model the system also very well. And this may be not so easy to do. We're going to get back to analytical modeling, and we're going to talk about some papers, but you have a good idea, hopefully, on that. So simulation is usually what we resort to as architects, because this really is very flexible. You can really simulate anything at some abstraction level. But there are, of course, trade-offs in simulation. And this is what I'm going to talk about. But let's talk about the other two over here also. Prototyping with a real system. This is definitely interesting. Like FPGAs, for example, provide a very good prototyping environment today. If you have an idea, for example, reinforcement learning-based memory controllers, you could implement an FPGA, and you could emulate a request going through that memory controller. You're bound by the limitations of the FPGA, of course. Whatever you do is bound by how much frequency that you can emulate or run the FPGA with, and also bound by other limitations of the FPGA. For example, what kind of cores can you actually put on top of that? It may not be, in the end, this is called prototyping. It's not really implementing the reinforcement learning-based memory controller, let's say, because that controller is not going to be designed to run an FPGA, perhaps. Maybe it's designed to run on a multi-core system, right? And you may not be able to emulate all of the effects of the multi-core system on an FPGA. So this is really good to do, but it takes, of course, a longer time. And real implementation, of course, you basically design this idea and put it on a real implementation and decide whether it's good or not. And this is the most costly, of course, and it becomes very hard to do it for many, many different ideas, right? If you want to decide whether an idea should go to your next processor, you don't necessarily implement all of the ideas and then pick the best ones, because you've already implemented and you paid the cost. So this is usually not a good way of really evaluating whether an idea will improve a target metric X. You want to do some of these things over here before you commit to a real implementation. That makes sense, hopefully. So as we go, basically the difficulty in architectural evaluation is really, the answer is usually workload dependent. The question that I posed earlier, it's usually workload dependent. And like caching, for example, there are cases where caching gives you 0% hit rate. There are cases where caching gives you 100% hit rate. And pipelining is another example. Any idea we talked about also, RAIDer, memory scheduling, whatever. And workloads change. They're not constant, as I said. You may be designing a system today, and that's going to be in use, let's say, that starts being in use after 5 years, because it takes 5 years to get it off the market. Depends on which company you are and what is your target, of course. And then it'll be used for 5 more years after that. So you're really targeting 5 years after, and that period for 5 to 10 years. And you don't know what workloads will execute. So you need to be very careful, clearly. And system also has many design choices and parameters, right? An architect needs to decide many ideas and many parameters for a design at the same time. So imagine implementing every single one of these. It's not going to happen. So it's not easy to evaluate all possible combinations. So how do you actually explore the design space becomes important. And also on top of the system, parameters can change. You may design a hardware accelerator for some reason. It may be used in some system, and that system's parameters, and it may also be used in some other system as well, right? Who knows? So basically, usually architects resort to simulation to explore this design space. It's easy to have a software simulator that you can configure that can give you answers with different system parameters. We talked about perfect bench prediction yesterday, right? That's hard to do on a real implementation. You could do it with prototyping, potentially, but you're limited. But if you have a software simulator, then you fake it, right? Whenever you get to a branch, you know exactly what the direction would be, and then you force the timing simulator to always take the correct path. Any questions? Yes?
Do you get better, more accurate results with simulation, or if you would implement it on an FPGA? Because
we'll talk about that, yes. Basically, accuracy is something that you need to be very cognizant about. It's not true that if you implement it on an FPGA, you will get more accurate results. You could have a very good simulator that provides you more accurate results. It depends on what you model in each. Okay, so basically simulation is really the field of dreams. As I see it, you really have many dreams, perhaps, and you want to evaluate whether your dreams are accurate or whether your dreams will pan out for somehow, right? An architect, as I said, in part a dreamer, a creator, right? And that's the mindset that we would like to have as an architect. And simulation is our key tool. Prototyping is also a key tool. This is not as much focused on prototyping, but if you have questions, we should really definitely talk about that, because that's very important also. And simulation enables many things. Basically, it enables the exploration of many dreams. Should I design a reinforcement learning-based memory controller, or should I design, I don't know, the latest idea that I have? Should I design a victim cache, or should I design a 32-way associative cache, right? Those are simple dreams, of course. You can have even more complicated dreams. Should I have processing in memory in this form versus in this other form? It also enables a reality check of the dreams, because you're trying to really check which dream is better. And basically it enables deciding which dream is better. But also it enables you a very convenient way to fool yourself with false dreams. If you don't model things accurately enough for your purposes, then you may actually decide, oh, this reinforcement learning controller is terrible, but it may actually in the end be a very good idea, which means that you actually lose the benefit of a good idea. Or the other way around, right? You may decide it's great, but then in reality it works terribly. Then you fooled yourself also. So you could make mistakes in both directions if your tool is not accurate. That's true for prototyping also. In prototyping you think a little bit more, so the probability that you will do something that's not implementable reduces, but the accuracy doesn't necessarily increase. So prototyping, as you go below, because you really have to think about how to implement it, the likelihood that what you will put down there is implementable increases, I think. But accuracy is a totally different question. You may actually have a very good analytical model that can get you better accuracy. Okay, so we'll talk about high-level simulation. You've been doing some RTL simulation, and it'll be done until at the end of this lab. You'll start with more higher-level simulation. The problem in high-level, basically, if the RTL simulation, the problem is it's intractable for design space exploration. It's too consuming to design and evaluate. So especially over a large number of workloads, and especially if you want to predict the performance of a good chunk of a workload on a particular design. Especially if you want to consider many design choices. So let's take a look at each of these over here. You have a large number of workloads, but RTL simulation takes very long, right? 1,000 instructions takes very long to begin with. Let alone a workload that has 1 billion. Well, 1 billion is a small number actually. Much bigger number of instructions. And yeah, if you want to actually change the system parameters, cache size associated with block size algorithms, then you have a big problem in terms of the explosion of the length of your simulation and the number of your simulations, both of them. As a result, if you're doing simulation at the gate level, RTL level, this becomes intractable. So usually people don't explore the design space with RTL simulation. RTL is done at a point where you actually decided the design parameters and what kind of structures you have. And at that point, you implement RTL to figure out how to actually implement things. Okay, a memory control and scheduling algorithm. I could keep adding different algorithms over here, right, and design choices. As you can see, we've covered a lot of these in digital circuits, but in order versus out of order execution. You don't want to do that. You don't want to build 2 RTLs for in order versus out of order execution, just to explore the design space. You could, but it always affects your cost and how long it takes for you to explore, right? Okay, so the goal in high-level simulation is to explore the design choices quickly to see their impact on the workloads we're designing the platform for. So what does that mean? So before we go into that, there are different goals of simulation. So one is what I just said. You want to explore design space quickly and see what you would like to implement, what you would like to do. Potentially implement in a next generation platform, or propose as the next big idea to advance the state of the art. These are actually similar but not necessarily exactly the same goals. Even within the exploring the design space quickly, you have potentially different goals, right? Like if you're writing a research paper, maybe you're not as concerned about the potential implementation in a next generation platform. You want to really propose an idea that's going to be effective 30 years later, and how do you actually do that? And how do you actually explore that in simulation? That's a bit different from the first one over here, but they have similar flavors. So in this case, the goal is mainly to see the relative effects of design decisions. With this new architecture, am I getting 10x performance? Maybe I'm not absolutely correct. Maybe I'll get 5x in the end if I consider every single design detail. But it's good to see the relative effects. If you get the relative effects correctly, maybe it's okay. Right? Because you're exploring design space quickly to prune out a lot of choices. And then you're going to zone into some of them and actually go into more detail. Another goal that's very different in simulation is match the behavior of an existing system. Like you already have a system that's implemented, I don't know, one of the processors that's running in my computer, for example, and you want to design a simulator that very accurately models what's happening there. Why? You want to potentially debug and verify that cycle level accuracy, right? Or you want to propose small tweaks to the design that can make a difference in performance or energy. In this case, you want to be matching the behavior of your existing system so that you can understand the relative effect of a small tweak. The goal in this case is very high accuracy. And this actually, well, companies do both of them. If you're designing a new architecture or microarchitecture, you can do both. But this is done a lot in companies that whenever you already have a design, now you can actually take the design and adjust your simulators that you built for the design to begin with to match that design. And you could do it at many levels. You could do it at the high level simulation. You could do it at the RTL simulation. And you want to be almost close to 100% accurate in this case. But no simulator ever achieves 100% accuracy on all workloads. I've never seen that like in companies where they have these big, let's say Pentium, whatever Intel calls it right now. They have RTL designs of these. And even those RTL designs are not completely accurate compared to the real system, because whenever you implement the real system, something changes during that implementation, and as a result, you don't match the RTL. So people actually try to correlate the RTL with the real system so that they can actually do this. Does that make sense? If you want to debug something, you really want to know match the behaviors of an existing system. Yes?
How does the real thing then change from the RTL? Do they not use the RTL to then generate the real chip?
Not automatically. Sometimes you go and do by hand, right? And once you do by hand, the designer doesn't necessarily obey absolutely what's in the RTL. Adds a cycle here or there, and then the thing is different. That happens a lot, actually. There's a lot of custom logic incorporated into the chips. If you automatically generate, yes, then you're relying on your tools. Okay. So there are other goals in between these also. One is you can refine the explored design space without going into a full detailed cycle accurate design. Cycle accurate means you're very accurate at the cycle level. But you want to refine the explored design space a little bit. Okay, you decide on out of order execution somehow. Should I have 64 reservation stations or 128 reservation stations, or should I do this kind of scheduling versus that kind of scheduling? That's another level of exploration. Or you can gain confidence in your design decisions made by this higher level design space exploration. Again, that's another goal. That's somewhere in between. Again, you explore the design space, you're going to the next level of detail, maybe. Okay, so you can imagine things in between. So there are trade-offs clearly. As I said, even here, the goal here is very high accuracy. Here, maybe you want to be very flexible so that you can explore many different design choices. Right? And this leads us to metrics to evaluate a simulator with. Basically, there are three major metrics. Actually, more than three, but I'm going to talk about three. We're going to talk about others in a little bit. Three major metrics to evaluate a simulator with. One is speed. How fast is the simulator? We're going to describe them in a little bit more detail here. Flexibility. How flexible is the simulator? How quickly can you modify it to explore the design space and ideas you have? And accuracy. How accurate is the simulator compared to a real implementation? Now, this is a bit tricky, of course, right? If you don't have the real implementation, if you're imagining a completely different architecture compared to what already exists, how do you even define accuracy? Because that ground truth doesn't exist. You have to work really with the basics and first principles to ensure that you're really accurate to what you could potentially implement. But even that is not necessarily correct, what I said, right? Because maybe you're really designing for a material that doesn't fully exist at this point and you don't know its characteristics. So that's the beauty of architecture, and that's also the danger of architecture. So there's a lot of art that goes into accuracy for sure. But also first principles, right? You don't want to violate some basics. So okay, let's talk about speed. Speed is how fast the simulator runs. This is some number of instructions per second or some number of cycles per second it can simulate, or slow down compared to a real system, if you can have the real system. These are some different ways of evaluating the speed of the simulator. Flexibility is how quickly can you modify the simulator to evaluate different algorithms and design choices. Hopefully that's obvious. And accuracy is how accurate the performance or energy or whatever metric you're trying to get out of the simulator that the simulator generates are versus a real design. This is also called the simulation error. And again, as I said, this real design is the dangerous thing here. That may not exist. Then you need to be very careful. But there's no other choice. You have to evaluate, right? Okay. So in general, these three metrics are very hard to optimize for, maximize at the same time. Right? You usually give up one, sometimes two metric to get to your goal. And depending on where you are, depending on what your goal is. Yeah, as I said, the importance of these metrics varies depending on where you are in the design process and what your goal is. Sometimes we don't care about accuracy as much, as long as we get the relative order right. Should I do in order versus out of order? If the relative order is 2x, I'll do it. So my simulation error maybe should not be more than whatever that 2x is right at that point in time, or whatever margin you put. So you should be careful in defining your goals also when you do this. Flexibility is very important, but it shouldn't come at the cost of either speed or accuracy actually, or your accuracy goal. And speed is clearly important, especially if you want to optimize your design choices, but again, it shouldn't come at the cost of too little accuracy. So usually it's a trade-off. You cannot get all of them at the same time. Okay, so how do you trade off speed, flexibility, and accuracy? Basically, speed and flexibility affect how quickly you can make design trade-offs, clearly. If you cannot run the simulation fast enough, you may be flexible, but it's not fast, that's not good. Right? Usually, flexible simulators are also fast because they take a higher level approach to simulation. They don't model every single detail. They actually get rid of a lot of corner cases. These corner cases, usually, whenever you design a system, to get it working correctly, maybe the last 10% of the cases take 90% of your time. And debug certainly takes a lot of your time, but maybe these last 10% of the cases in your instruction set architecture or whatever design you have take 90% of your time, but they're not the common case. Maybe they're seen 10% of the time. Right? So you always need to trade off, okay, this take 10% of the time, but if I really implement them in my simulator, it's going to take 90% more time. Do I really want to implement them? It depends, and the answer depends. Do you really see those 10% in your workloads? If you do, maybe you should implement them, right? If you don't, then it's a good idea to not implement them probably. Then the question is, how do you decide whether you see those 10% or whether you are going to see? That's where the art and expertise comes in, and that's the difficult part. Okay, accuracy of the simulator, how good your design trade-offs may end up being. Basically, that's affected by the accuracy clearly, right? Because if you're inaccurate in the simulation and that affects what you're examining, then you may actually decide to do in-order execution, whereas out-of-order execution is the right answer. Right? That sounds not good. And also accuracy affects something that we didn't discuss, but I'm going to introduce now, which is another metric, which is the simulator design time. Basically, how fast can you build your simulator? This actually is really important too, because if you want to really explore the design space quickly, you cannot afford taking 2 years to build a simulator. If you do, then your competitor is already ahead of you, right? And this has actually happened. I've seen this in many companies. If they take too long to build a reasonable simulator, they can actually end up being late in their designs. This also, of course, this is not only accuracy, but it's also software engineering, how complex you approach the software. Because in the end, simulator is a piece of software. And architects actually are very good software engineers. This is one of the reasons these big companies like hiring architects and maybe using them as software engineers. But basically, there are a lot of software engineering choices that you make over here in your simulator that could affect your not only accuracy, but design time. For example, do you actually have a single-threaded simulator, or do you have a multi-threaded simulator that's extremely parallel? That affects your speed. Well, I've seen both, and sometimes if you actually do the multi-thread simulator, it becomes very hard to debug. That affects your design time, and that affects your speed of modification, I should say. Which means it's your flexibility. Okay, so there are interesting design choices here. Flexibility also affects how much human effort you need to spend modifying the simulator. If the simulator is very flexible, it's easy to use, then it's very good. Okay, basically you can trade off between these three above to achieve the design space exploration and decision goals. And you need to pick your goals, of course, first. So high-level simulation, in high-level simulation, the key idea is to raise the abstraction level of modeling compared to RTL, to give up some accuracy, to enable speed and flexibility, and quick simulator design also at the same time. That's what, in general, we call high-level simulation. There are many examples of high-level simulation, and you can argue which level. We're going to talk about that. The key advantage over here is you can still make the right trade-offs and can do it quickly. And all you need is to model the key high-level factors. You can omit corner case conditions, as I said earlier, right? If, for example, if, for example, your page table walks are not happening a lot in the workloads that you have, maybe you don't model them, right? I'm just picking a random obvious one. But it all depends on whether you have them in your workloads or not. And if you don't model something, what do you do if you think it might be happening on your workloads? Well, you add a counter in your simulator. You detect that, oh, this thing that I'm not modeling is actually happening a lot. Increment the counter. Right? If it happens really a lot, then maybe it's time to model it. So you can actually design catches in your simulator such that the simulator itself catches, oh, you may be perhaps modeling this, right? You could actually have that even more strict, right? If some value is greater than 10%, let's say, your threshold, then the simulator says, oh, I'm not running this for you. And then you can go back and either override your simulator or overwrite your simulator such that it actually models it. Okay, so that's the key idea over here. And there are many, many examples of this, right? Basically, all you need here is to get the relative trends accurately, not the exact performance numbers. And this is really important, actually, because if you really were concerned with exact performance numbers in your design space exploration, you may not be able to make any progress into the future, right? Like you in the seminar course yesterday, you talked about systolic arrays, and there was zero evaluation. There was zero evaluation in that paper, right? Although there are other papers that had evaluations, but those were not exact evaluations also, actually, in some other papers. But we know that that idea actually affected many, many designs. Systolic arrays actually are implemented today as accelerators. So basically, if you get the relative trends right, then you can actually enable progress. You don't need to be exact in progress. I mean, you may not even have any of the evaluations, actually. Okay, so the disadvantage is, of course, if you simulate this way, now you open up the possibility of potentially wrong decisions. Right? And you need to, the goal should be to avoid this as much as possible. Okay? Basically, the key question over here is how do you ensure you get the relative trends accurately? How do you ensure you're not wrong? Okay, so another view of simulation is the view of progressive refinement. Basically, you start with this high-level models, let's say very abstract. I put C over there, but it could be in any high-level language. Usually, high-level models are written in high-level languages so that you can actually be more flexible. And then you develop them, and then you evaluate them, and then you refine them later, develop more medium-level models. They're less abstract. And then you basically decide on some choices, and then go and write low-level models for them, RTL, let's say, with everything modeled. And then from that, you take it to a real design. So that's one way of actually designing, let's say, a processor. You start with this, and progressively, you make design choices that will eventually bring you to a real design. Not all projects end that way. Some projects are cut before the real design happens, because maybe you made the wrong choices or you were unlucky because the trends have changed over time, right? And as a result, your project is not interesting to some people in the world. That happens. But assume that you get here, then hopefully you've enabled this real design, because of what you did at the higher levels to begin with. And actually, if you look at companies like Intel, AMD, NVIDIA, or whatever manufacturer you have, Google, they all have these different levels of models, right? You start with high-level model first, though, usually. Okay, once you have the real design, actually, so you progressively refine going from top to down. But once you have the real design, you have a unique opportunity, which means that you can go back and progressively refine backwards, right? Higher levels. Because now you have the real design, you know where your RTL is not accurate, or how much your RTL is not accurate. You can say, okay, I'm going to make it a little bit more accurate. You know where your medium level model is not very good in some cases, then you can figure that out. And you can say, okay, I'm going to tweak it this way. I'm not going to lose the abstraction level, but I'm going to do these tweaks such that it better matches the real design. And that enables you to actually leap forward and have a more accurate model without actually losing the abstraction levels. That's actually very beautiful, because now you've figured out the mistakes of your simulator and you can loop back. So as you refine, as I said, you go down the above list, abstraction level reduces clearly, and accuracy hopefully increases, but not necessarily if you're not careful. So if some of the medium level models actually can be less accurate than some of the high level models, this is very interesting. For example, you may actually design an energy model for a processor where you count every single event and you associate energy costs with every single event that happens. And at the end of the simulation, the total energy you get would be sigma event times the energy cost of the event. Right? Basically, you have a weighted sum of the energy of all the events. That's one way of modeling energy in simulation. You simulated the processor and you have all the events and you have event counts. You multiply each event count with the energy cost associated with that event. Would this be more accurate than a high-level model that basically, I don't know, let's say associates some sort of activity of the processor? How often is the processor active? How often is the memory active? And associates a high-level energy, average energy cost with each, and then multiplies only those two. It turns out sometimes those high-level models are actually more accurate, because counting these individual events are not necessarily accurate, because you may miss some events. And if you miss those events, that's not good. Whereas if you have a higher level model with the appropriate numbers, you can much more quickly get more accurate numbers. So it's very important to be careful about this. There were actually examples of this. There were works that were done in industry as well as academia that showed that, oh, if you have a higher level energy model, you're actually more accurate. So we should use these high level models, because they all have other benefits also, clearly. Okay, so you should be careful about this, clearly. So flexibility, clearly, when you go from top to down, reduces. And speed of simulation also reduced, except for real design, because real design is not simulation anymore. And as I said, you can loop back and fix the higher level models. So this is very interesting. It's good to be able to do that looping back. Okay, so making the best of architecture. Basically, a good architect is really comfortable at all levels of refinement. If you go back at all levels, including the real design, designing the real architecture or real system, but also at the high level models as well, because then you can actually do all of this, right? And, well, including the extremes I said. And it's important to know when to use what type of simulation, of course, right? For example, if you're doing design space exploration, you don't want to do prototyping for all of the examples, designs that you can generate. And more generally, what type of evaluation method? If you can do analytical modeling without simulation, that's good, but it's important to be very careful about that decision. As I said, there are a variety of evaluation methods available. So not only the extremes of the simulation, but extremes of the evaluation methods are really important as well. Okay, any questions? No? Then I'm going to talk about a simulator very quickly that we've developed. This was actually developed over the course of, I don't know, 10 years or so. We first started initial incarnations of it, not very accurate to begin with while I was at Microsoft Research, and then my research group took over at CMU and they actually developed new incarnations of it. So history, of course, helps simulation. If you have a lot of experience, it's good to make use of it and develop better simulators going forward. I'm not suggesting this is the best simulator, but this is one of the best simulators that are out there to simulate memory today that are used by companies Actually, many companies use it. They contribute to it also, as well as academia. But what was our motivation to develop this? Basically, as you know, the DRAM and memory control landscape is changing. There are many new and upcoming standards and many new controller designs. What we wanted to have was a fast and easy to extend simulator that's also reasonably accurate. Actually, in the end, we're going to be very accurate, at least at the DRAM level. And it's an example from the paper. We're going to cover some of these. We're going to talk about 3D stacked architectures, for example. But there are different kinds of DRAM, commodity DRAM, low power DRAM, which you were exposed to last week, graphics DRAM, performance, high performance DRAM, 3D stacked, and many academic proposals, especially more recently. And the paper was written in 2015, so these things end at 2015, as you can see. So how do you actually model all of these and make design decisions between them? And again, your goal may be different, right? Your goal may be to develop the next big academic design that's going to outperform everything in some metric. Or your goal may be, I have this workload and I have this system that I can model somehow. Which memory should I use? Those are two different goals. And the simulator caters to both of those different goals. Of course, if you want to model your next big academic proposal, you should go ahead and change the simulator. But if you actually want to just make a decision, maybe you don't need to change the simulator that much. So basically, Ramulator is a simulator that provides out-of-the-box support for many DRAM standards. And I'm not sure if this is up to date now. There are more that are out there. And at the time we wrote it, it was 2.5x faster than the fastest open source simulator. I don't know how fast it is. It's good to do these studies again, perhaps. It's modular and extensible to different standards. And it's good to look at, like these are some evaluation metrics, for example, and these are comparisons to other main memory simulators that were there at that time when the simulator was written using 2 traces. So you can see this is the number of cycles that were simulated. So they're similar. You want to simulate similar cycles. And this is the runtime of the simulator. That's one metric to evaluate the simulator with. You can see that Ramulator was pretty fast at the time. It's still pretty fast, I think. And this is the requests per second that were simulated in terms of runtime. So this is kind of correlated clearly. And this is the memory consumption. So that's another metric you could potentially evaluate the simulator with. How much memory does it consume? Right? You don't want it to consume a lot of memory because that does affect your simulation bandwidth in the end, because usually whenever you do these simulations, you farm out a lot of simulations to many machines. And if your machines cannot fit many instances of your simulator, then you have a problem, right? Okay, so this is one example study that this sort of simulator enables. And this is a high-level simulator, although it does model the standards reasonably accurately, but it does model it at the C level. It doesn't go into the gate level detail. It basically associates how long the timings with actions, and it basically models that timing as cycle counts in the simulator, as opposed to, okay, I'm implementing this gate that's going to do this, right? If you do that, then you're not going to be able to do any of these studies because every one of these will take a long time. Okay, so this is one example, and I'd recommend that you read the paper, but I'll give you the power of such simulation. Basically, you can model all these standards. These are different DRAM standards, DDR4, sub-area level parallelism, low power DDR, graphics, high bandwidth memory, 3D stacked memory, wide I/O. These are three different 3D stacked memory standards. And basically, this is one experiment that you could do. This is IPC instructions per cycle, normalized to DDR3, which is this baseline over here, across 22 workloads. And there's a simple CPU model. If you want to get IPCs, you need to have a simple CPU model. And if you look over here, these are the different characteristics of the different standards. DDR4, for example, has higher bandwidth enabled to the CPU, but it also has higher latencies. And you can see the bandwidth number over here. And if you look over here, high bandwidth memory has much higher bandwidth because of the data bus, as well as lower timings, lower latencies. So I could, this rate is in terms of mega transactions per second, and each transaction is bigger here, as you can see. That's why you get higher bandwidth. Okay, anyway, we don't need to go into the detail, but this is one example study that you could do. For example, what this shows is in a YLM plot, the relative instruction per cycle improvements of DDR4 over the baseline DDR3. What does this mean? This is the benchmark that gains the most. Its performance improves by, I don't know, maybe 40% or so here. And this is the benchmark that gains the least. Its performance improves by 0%. And this is the average, maybe 10% or so over there. So DDR4 basically improves performance by about 10% on average across these workloads. There are interesting things that you can figure out. This is the idea of subarray level parallelism, which I briefly mentioned. Basically, you enable pipelined accesses to subarrays within a bank. Normally, whenever you get a bank conflict, to be able to access that bank, you need to wait for that bank to become free. If you have the idea of subarray level parallelism, which we published in 2012, then the idea is you have these subarrays inside a bank, and you slightly modify the circuitry such that whenever you get a bank conflict, if the first access goes to, if the second access goes to a subarray that's different from the subarray that the first access goes to, you can start the second access in a pipeline manner. That way you overlap the latency of the first access and the second access in two different subarrays within the same bank and overcome the latency issues with bank conflicts. And it turns out that improves performance significantly. And you can read the original paper that also shows that. And these are the average numbers, average improvements. Okay, that's 19%. This was 14%, as you can see. And there are also interesting things like LPDDR, low power DDR actually reduces your performance on these workloads on average. It's LPDDR3 reduces your performance by 12%. And you can go back and figure out why your bandwidth is the same compared to DDR3, but your latencies are higher, as you can see. And high bandwidth memory in these workloads actually does pretty well. As you can see, it improves performance by about 27%. And the top part is actually cut off maybe over here. So the benchmark that improves the most actually improves a lot. So this sort of studies can be enabled by high-level simulation, as you can see. Right? If you were to go ahead and implement all of these in a real system, good luck. First of all, there's no real system that can implement all of these. There are a lot of issues because these are all different memory technologies. You cannot actually do this study on a real system in a controlled way. Because maybe there's a system that implements DDR3, that memory controller. Maybe there's another system that implements HBM, but these are completely different systems. You're comparing apples and oranges, basically. Actually, in this case, there's really no way of doing this study on a real system. You could say, okay, I do it in a prototype, in a memory controller, in an FPGA. Okay, maybe you design the memory controllers for these. The problem is that not just the memory controllers, but all of these have different interfaces, analog interfaces. So you really need an FPGA that has all of those analog interfaces. We discussed this actually in the last memory lecture. Right? In order to design a memory controller, it's not just the memory control logic, but also the analog interface. And if your analog interfaces are completely different over here, again, you cannot build a prototype system for this. So you actually have to do simulation in this case if you want to do this study. And I don't know about theoretical proof. I don't think you can actually do any of this with analytical modeling easily. Okay, and this is their emulator paper and source code. If you're interested, you should take a look at it. It's being developed and it's being improved a lot. And we support it, and people actually use it. As I said, these are used by some big companies and also academics. Okay, this is an extra credit assignment. You can review the emulator paper. It will be on our review site, but it's not a required review. It's actually a short paper, only 4 pages. And you can download and run it and repeat some of the studies. And you can upload your brief report to Moodle if you're interested in this. And this may be part of a future homework, but we haven't decided that yet. We should first finish the existing homeworks. Does it sound interesting? Okay. So that's the end of the simulation lecture. Any questions? I think it was important to cover this, especially before your 3rd and 4th lab assignments that are going to come, which will be in high-level simulation. And maybe we'll have a emulator lab assignment or a short assignment. Any questions? Thoughts?